All right. So paired t-test, the first step is a hypothesis for the test. So we're starting on averages. So we start using means, we're looking mu, and we're looking at the mean of the differences, and we're trying to see if those are different from 0. So this doesn't have to be a 0, but most of the time it will be. This little d right here, most of the time you want to write how you're subtracting things. So like yesterday we did the temperature example, where we did July temperatures minus January temperatures. If I was doing a test with that data, I'd want to write July minus January, just so that you could show how you were subtracting. Okay? So you can always substitute that in. After you do the hypotheses, well, so that's your null. Your alternative then is then that the differences are greater than, less than, or not equal to 0, like it always has been. After you do the hypotheses, we have conditions. All those conditions from yesterday are what we're using. Why is the data paired? Is there independence between individuals or subjects or whoever we're talking about? Randomization, 10% if you can fit it in, if it makes sense. And then nearly normal, right? If all those conditions are met, we can continue with a paired t-test. The mechanics are essentially the same as a one-sample t-test. So again, in your calculator, if you were trying to check your answer, you would use a one-sample t-test, because paired t-test is not in there. It doesn't exist. Okay? So if you're doing a hypothesis test, you're doing the mechanics, you find 3 things. You find the standard error. The standard error is just a standard deviation of the differences. Okay? So the standard error is the standard deviation of the differences divided by the square root of n. Remember, n is the number of pairs. So if you have more than 10 individuals, whatever, if you have 20 individuals but they're paired, you have 10 pairs. So make sure n is the number of pairs. So we have our standard error equation. Then we're trying to find our test statistic. We're still looking at means, so we're still using t. So just like always, we have our statistic minus our parameter over the standard deviation of the statistic. So our statistic is the mean of the differences minus what we think the mean of the differences is, which probably is going to be 0. We wrote that in our null hypothesis, over the standard error that we found before. Now, if you're finding t, you're going to get a t statistic. And after that, you have to find, your third step is the p-value. How are you going to find the p-value once you have the t statistic? How do we find p-value? TCDF. So use TCDF. TCDF is going to ask you for degrees of freedom, right? So the degrees of freedom in this case are n minus 1, number of pairs minus 1. Okay, so then we can get our p-value. Then the last step is to make your conclusion. Your conclusion is the same that it always is. Your p-value is high or it's low. So do you reject or do you fail to reject? And what is that evidence of or not evidence of? Questions about the mechanics. All right, then I've got one example. So in chapter 24, I brought this example up and we talked about why we couldn't do it. All right, this job satisfaction index situation. A company institutes an exercise break for its workers to see if it will improve job satisfaction, as measured by a questionnaire that assesses worker satisfaction. Scores for 10 randomly selected workers before and after the implementation of the exercise program are shown in the table. So we talked about in chapter 24, we couldn't do a 2-sample t-test because the 10 workers aren't giving, you have one sample, right? You have 10 workers that are independent, but the information isn't independent of each other. It's paired. Okay? So A just says identify the procedure you would use and then check the condition. Again, once we get into this chapter, you have to stop and think, Is it a 2-sample t-test or a pair t-test before you move forward? Okay. So this is a pair t-test, and if we go through the conditions, the first one we have to do is justify why it's paired. So why is the data paired here? Yeah, we have 10 people with 2 job satisfaction scores, right? So the scores are paired by individual. Next condition, independence. Is each worker assumed to be, can we assume each worker is independent of the other? You could assume that. It says the 10 are randomly selected workers. So randomness has been employed. 10% is, are these 10 workers less than 10% of the workers at the company? We're going to assume so, probably, right? It's a decent sized company, that shouldn't be a problem. And the last one is your nearly normal condition. How am I going to check that? What do I have to do to check that? If you look at a graph, what are we looking at a graph of? The differences, right? So I'm going to need to type in the before and the after information into my calculator, and then make a third list of the differences. So it's very important, if we're all going to be on the same page here, to decide if we're doing before minus after or after minus before. It doesn't matter. They're trying to see if the exercise program improves worker satisfaction. So they're trying to see if the after score is greater than the before score. So I might do after minus before, so it would be positive, but it doesn't matter as long as you think that through. So are you guys going to do before minus after or after minus before? Okay. So in your list 3 then, you would have to do, if this was list 1, list 2, you have to do list 2 minus list 1 if you're going to do after minus before. Okay? Do before minus after, that's also fine. You just need to keep track of that because that will affect how you write your hypotheses in part B. I already have this data in my calculator. So stat, edit, it's all in there. List 3 I did after minus before earlier this morning. So if we look at a plot, again, I use a normal probability plot because if it's straight, then it's nearly normal, it's approximately normal. If it's not straight and there's curves, then I know it's not. But it's very straightforward. So is a normal probability of plot of this set of differences reasonably straight? Yes. So that condition has been met as well. So because the conditions have been met, we can perform what kind of test? Paired t-test. All right. So B says to actually test the hypothesis and state your conclusion. So we need to write some hypotheses. We're talking about the mean of after minus before. And if we didn't think it helped at all, then the change would be 0, right? They would score the same thing both times. Do we want the after score to be larger or smaller? Or sorry, I guess higher or lower. That would make sense. We're talking about job satisfaction. We want the after score to be higher, right? Because we want to improve job satisfaction. So we're assuming after is higher, then after minus before should be greater than 0, right? Now make sure you think through this type of thing, because if you're talking about time, for example, if one being faster than the other, then maybe you're looking for negatives. Okay, so just make sure you think through the scenario. Any questions about our hypotheses? Again, notice I don't have 2 different mu's. I have 1 mu with a difference. We already checked the conditions, right? So we can do the test. We're doing the mechanics part now. So here's your hypotheses. We already did the conditions in part A, so now we're going to do the mechanics. So we're going to find our t statistic. Now, in order to do that, I need to know the mean of the differences and the standard deviation of the differences. So how can I find those 2 numbers? I can look at 1 variable statistics in my calculator. I can look at list 3, and it'll give me that. So I have a mean difference of 8.5 and a standard deviation of 7.47. All right, so if I do this, my t statistic, I have my mean difference, so 8.5, minus what I think the mean difference is, which I'm assuming is 0, in the null hypothesis, divided by the standard error, which is the standard deviation of the differences, over the square root of n. N is the number of pairs I have, which was 10. So I've got 7.47 divided by the square root of 10. That's 2.36. And then I've got 8.5 minus 0, so 8.5 divided by that answer. So about 3.598. Once I have the t statistic, I can use TCDF. 3.598 to infinity because we said it was greater than 0, so we're looking for the upper tail. There's 9 degrees of freedom, 10 pairs minus 1. We get a p-value of 0.003. So now we're going to make a conclusion. Is our p-value high or low? Low. And so if it's low, what do? Reject. So we reject the null hypothesis. So if we reject the null hypothesis, that means there's evidence of what? That job satisfaction increased after the implementation of the exercise program. Right? So it was low, we rejected it. Part C just says, if your conclusion turns out to be incorrect, what kind of error did you commit? So if we rejected incorrectly, what kind of error is that? Type 1 or type 2? Type 1. Right? You reject a null hypothesis is actually true. All right. Questions about that?